Alright, so let's take a look at the area of the region between two curves. So we're going to look at the area between two curves, so that'd be like, the function, the x-axis, and then the area between two intersecting lines. So you have two problems, and then your AP standard is to be able to find the area of the region between curves and apply this technique to solve problems. So application, there's a lot of applications, and later on when we find volumes, this is extremely important. So there may not be many like that directly between two curves or intersecting lines, maybe one or two questions, but finding the volume is extremely important. In order to find the volume, you need to be able to do this skill as well. So let's take a look at this, what this looks like. So first of all, the wording is extremely important. Like on this first one, it talks about the area. It talks about the area between the region between F and G. So the region between F and G, okay, is this region here. So if you're going between the dotted lines, it's this region here. Okay, that's between F and G. Now, if you're looking under F, so F is your upper function, it's just this. So G doesn't even matter in this case. And then the last one, the area of the region under G. So your G is your lower function, so it's going to be this area. So G is just that area there. That's not the prettiest, but you get the idea of where you're integrating. The wording is extremely important, so be careful. Alright, so that's what this means. So the integral, this is what this section is all about. F of x, which is your upper, okay, minus g of x, which is your lower function. As you can see here, f is your upper and g is your lower. So you could even plug in here f of x minus 0 and g of x minus 0, because it's really you're integrating to this line where y is equal to 0. Okay, so let's take a look at an example. So this example says find the area bounded by the graphs of y equals, so I have this picture here for you, y equals x squared plus 2 and y equals negative 2. So this is x squared plus 2 and this is negative 2 here. And so first of all, and x equals 1. So we also have to draw a picture of a graph here. So really, excuse the bar, I'm going to erase this, but that's the area that we're finding. So just think of that. Alright, so this rectangle, we have to find the area of one of these rectangles. And so the height of this rectangle is your upper function minus your lower function. Okay, so the height is your upper minus lower. That's where we get the f of x, which is your upper, minus your lower. And so it's going to be x squared plus 2 minus your lower function, which is given to us as negative x. Now we're going to be integrating that, and this is with respect to x, so we sweep left to right, and so the integral is from 0 to 1, and that's with respect to x. So it's all that times dx. And so when we integrate that, we can simplify this. That's just plus a positive. And then when we integrate it, you would have the x squared plus x plus 2, and so that would be, oops, let's get rid of the integral here because I'm actually going to integrate it. There we go. So when I actually go and integrate it, you would get x to the third over 3 plus x squared over 2 plus 2x. And then your limits, remember, are from 0 to 1. So you're going to plug those limits in. When you plug your upper limit in, you get 1/3 plus 1/2 plus 2. And then when you plug your lower limit in, all of that is 0 anyway, so that's not going to matter. So let's go ahead and just simplify this. Common denominator of 6, so you'd have 2/6 plus 3/6 plus 12/6, and all of that, when you simplify that, that equals 17/6. So that gives us the total area trapped between all of these curves. Your upper curve, which is the x squared plus 2, your lower curve, which is negative x, and then between your y-axis and x equals 1. Let's go ahead and try another one here. So we're integrating, and we're finding the area trapped between these two curves here. You have f of x, which is your upper function, and g of x, which is your lower function. And so your integral is going to be between their intersecting points. Your leftmost intersecting point occurs at -2, x equals -2, and your rightmost intersection point occurs at x equals 1. And so that means that your integral is going to go from -2 to 1, and it's going to be your upper function, which is this function here. That's your f of x, so that's your 2 minus x squared, minus your lower function, which is just x. All of that times the change in x. And so when we integrate this, we can go ahead and integrate it. The integral of 2 is 2x, minus the integral of x squared is x to the third over 3, minus the integral of x, which is x squared over 2. And your limits are from -2 to 1. You're going to plug 1 in there, and when you plug 1 in there, you get 2 minus 1/3 minus 1/2 minus your lower limit. Always put a parenthesis when you put your lower limit in, because you're subtracting all of that away. And so when you plug -2 in there, you get +4, and then you're going to get +2/3. Sorry, not +2/3, +8/3. My bad. Because that's going to be -2. No, yeah, so it's positive, and then it's going to be -4 halves here. Then when you simplify that, here, this becomes a plus, that becomes a negative, negative, plus, once you distribute that negative in. Then looking at this, when you put like terms together, all that jazz, you end up with 8 minus 9/3 minus 1/2. Okay, so this becomes 3. So 8 minus 3 minus 1/2 is 4 and 1/2. Okay, so then that would be the area trapped between these two curves. If I beautifully draw this in, that would be the exact area trapped between those curves. So this finding the area between two curves is extremely important, because in a couple sections we're going to be taking this area and spinning it and creating a three-dimensional model. In this case, I think, let's say you spun it around, let's say this dotted line is your axis, I think you'd make an angel. So if you spun it around here, looks like you make a pair of wings, so they'd be angel wings. That's kind of cool. Anyway, let's move on. Looking at this one, you're looking at the sine and cosine curves. Again, go ahead and try this on your own, see how you do, and then come back and check your answers. But you notice the sine and cosine curves cross each other an infinite amount of time. So what we want to do is just find one of those regions. And so one of those regions is going to look like this, and they're all going to be the same, so it doesn't matter. So first off, we need to figure out where they intersect. And so where they intersect is where they're equal to each other. So we're going to set the sine of x is equal to the cosine of x, and we're going to find the first two solutions. And the first two times where they're equal to each other is, well, the first time is at 5 pi over 4, or sorry, pi over 4, and the second time is at 5 pi over 4. So then those are our limits. We go from pi over 4 to 5 pi over 4. Those are the limits there of our integral. And it's going to be your upper function, which is in this case from pi over 4 to 5 pi over 4. It's your sine of x minus your lower function, which is cosine of x, all times dx, like that. Okay, we can go ahead and integrate. And when we integrate that, you would get, I'm going to come over here, negative cosine of x minus sine of x. Then your limits are from pi over 4 to 5 pi over 4. Okay, then when you plug your upper and lower limits in, let me just go right underneath your upper limit, so it'd be negative cosine of 5 pi over 4 minus the sine of 5 pi over 4 minus parentheses. Now you're going to put pi over 4 in there, so it'll be negative cosine of pi over 4 minus the sine of pi over 4. You need to distribute, be really careful. You need to distribute this negative in, so this becomes a positive, this becomes a positive, and this becomes a positive. So now what you can do is you can simplify. So this is negative radical 2 over 2. This becomes, negative negative, so that's positive. Negative negative again, this becomes positive radical 2 over 2. Then you would have plus, then you would have radical 2 over 2 and radical 2 over 2. So if you do this, you'd have here on the left side 2 radical 2 all over 2 plus 2 radical 2 over 2, which then simplifies, these cancel, and you'd have radical 2 plus radical 2, which is 2 radical 2. That's confusing. So if you need to, just, pause it and go back and try it again, whatever. But your final answer is 2 radical 2, and that gives you the area between the sine and cosine curve, between their intersection points. Okay, so if we look at this one, it says to find the area of the region between the graphs of f of x and g of x. So, you have your f of x function and your g of x function. You notice here the key point, the key thing to identify is, so between negative 2, x equals negative 2 and 0, you have this function, whatever, I don't know, this is f of x, is your upper function, but between 0 and 2, g of x is your upper function. So you're going to have to take two different integrals. Your first integral is going to be from negative 2 to 0 of f of x minus g of x dx, and then you add that to your second integral, which is from 0 to 2 of g of x minus f of x. So you have to set this up as two separate integrals. So remember, f of x is 3x squared minus x. First of all, go ahead and change this. Nice to notice this should be to the third. It's 3x to the third. Because looking at f of x, which is the 3x to the third, that's cubic. So this needs to be 3x to the third. Alright, so when you take 3x to the third, that's f of x, minus g of x, which is negative x squared plus 2x, you get 3x to the third minus 12x. And then your limits are from negative 2 to 0. Your second one, when you take g of x minus f of x, you end up with negative 3x to the third plus 12x. All that times dx. Alright? So now once you get here, it's straightforward integration, so we're going to go ahead and integrate. So this first one, you'd have 3x to the fourth over 4 minus, you'd have 12x squared over 2, which simplifies to just 6x squared. Okay, and that goes from negative 2 to 0. Over here, again, you'd have negative this time, 3x to the fourth over 4, and then plus 6x squared, and then that goes from 0 to 2. So we set up those two different integrals. When you plug 0 in, you notice you just have 0. So it's just going to be your upper limit, which is just 0, minus your lower limit, which is going to be 3 times 16 all over 4, minus, this would be 6 times negative 2 squared is just 4, plus, when you plug your upper limit in, it's going to be negative 3 times 16 all over 4, plus, then you would have 6 times, not 8, but 6 times 4 here, minus, when you plug your lower limit in, that's just 0, so that's, you can just change that to 0. So when you simplify here, that'll turn into a 4, that'll turn into a 1, so you can see that you have 12 there. Same thing here, that's a 4, that's a 1. Okay, so you would end up with this negative on the outside, so then you would end up with 12 minus 24. Then you would have plus, and on the other side, you'd have negative 12 plus 24. And when we distribute this negative in, it becomes negative 12 plus 24 minus 12 plus 24. So then when you simplify all this, it equals 24. So you can check your answer, see how you did, and then we'll move on to the next problem. This one says that find the area of the region bounded by the graphs. To give you two graphs, this is referred to integrating with respect to y. Now, let me go over a few things. This is integrated with respect to y for two reasons. The main reason, the most important reason that you have to remember is that with your Riemann sums, your little rectangles, okay, are perpendicular to the y-axis and parallel to your x-axis. So if your little rectangles are ever perpendicular to your y-axis, then that means that it's with respect to y. So what that means is that your integral, everything in your integral has to be in terms of y. That is extremely important. I cannot stress that enough. So when we set up our integral, that means no longer are we sweeping this function from left to right, but rather from down to up. So then our downmost point where they intersect is at y equals negative 2. So then in our integral, that is going to be our lowest value. So that's going to be our lowest point of integration. So from negative 2 to up here, you notice it goes all the way to 1. Now, to find the height of the rectangle, you go from this point to that point. So you always go from right to left when you're integrating with respect to y. That's extremely important to remember, not only for now, but when we find volumes of solids that are spun around the y-axis, you always want to go from the furthest y function left. Okay, so if you think about the furthest y function, looks like it's going to be your 3 minus y squared function. So it's going to be 3 minus y squared minus, in parentheses, the y plus 1. Now, if you look at this, it's a little tricky, but it's with respect to x. And that's fine. All that does is, change, flip it, basically, which is fine. So then our differential is going to be, instead of dx, it's going to be dy. So here's our integral. That's the biggest part. Everything else is the same as before. If they're like terms, by all means, put them together. Like here you'd have 3 minus y squared minus y minus 1. Then you can put the negative 1 and the 3 together. So you'd have the integral from -2 to 1 of just negative y squared minus y, and then plus 2. And then all of this times your dy. Now you can go ahead and just integrate it. And when you integrate it, it would just be negative y to the third over 3 minus y squared over 2 plus 2y, and that is from our limits are -2 to 1. So all we do is plug 1 in, then plug -2 in, and when we plug 1 in, you get -1/3 minus 1/2 plus 2, and then when you plug -2 in, you would get 8/3 minus 4/2 minus 4 equals. So if you look at some of this, okay, the +2 and the -4 could go together, and even this right here, because really this is just -2, so those cancel, and so you're left with just -4. Then also the 8/3 and the -1/3, so that gives you +7/3. And so basically what you're doing is taking +7/3 plus -1/2, and then when you simplify that, that gives you 9/2. That should be your final answer. 9/2. Now, same function, okay? With this part, we're taking it and finding the integral with respect to x, which is what we're used to, and that's fine. However, if we look at this, there's a problem. Your upper function is y equals x minus 1 up to this point. So it goes from -1 to 2. There's a 2. And then your upper function is x minus 1. And your lower function is negative square root of 3 minus x. And that's dx. And then your lower function, so that's where it stops. So that's where it gets tricky, is that if you do this one with respect to x, you have to set up two separate integrals. And so your second integral is going to go from 2 to 3. It's going to be your upper function, which is the square root of 3 minus x, minus your lower function, which is the negative square root of 3 minus x, and all that times dx. So it's your upper function plus your lower function, and you have to do it two integrals, because you notice if you draw your rectangles vertically, it splits right here, where this function then, well, stops existing really, and then you have this function as your upper and this one as your lower. Alright, so sometimes you have to be able to recognize, do I use y as my variable, or do I use x? Do I use my rectangles perpendicular to the y-axis, or do I have my rectangles perpendicular to the x-axis? You just have to be really careful with that. Alright, and so to finish this one, just take my word for it. The answer is the exact same answer as we got up here, just with a lot more work. As you can see, it's going to be a lot more work, but it would be the exact same answer. So just be able to recognize if finding the integral with respect to y or finding the integral with respect to x would be the easiest method. So that's it for these notes. So just to sum up, you should be able to find the area of the region between 2 points, and then also between intersecting lines, I should say between 2 curves, and then intersecting lines as well. And then also understand the difference between with respect to x, which is the vertical rectangles, and with respect to y, which is the horizontal rectangles.